এপ্রিল 2020 সেমিস্টারের আইসিটি 6900 স্পেশাল টপিকস ইন আইসিটি অ্যাডভান্স মেশিন লার্নিং কোর্সের লেকচার 5-এ সকলকে আমন্ত্রণ জানাচ্ছি। Today's topic is neural network representation. Today I am going to discuss about a learning algorithm called a neural network. We are going to first talk about its representation, and then in the next set of slides we talk about learning algorithm. In fact, in another lecture we'll talk about learning algorithms. Neural network is actually a pretty old idea but had fallen out of scene for a while, but today it is the state of the art technique for many different machine learning problems. Now, why do you need yet another algorithm when we already have linear regression and logistic regressions? So the question is, why do you need to know neural network? Consider a supervised learning classification problem where you have a training set like this one. If you want to classify between 1 and 0, one thing you could do is to apply logistic regression with a lot of nonlinear parameters like this. So here g as usual is the sigmoid function, and we can include lots of polynomial terms like these. And if you include polynomial terms, then maybe you can get a hypothesis that separates the positive and negative examples as shown in the figure. This particular method works well when you have only say two features x1 and x2, because you can then include all these polynomial terms of x1 and x2. But for many interesting machine learning problems would have a lot more features. And suppose you have a housing classification problem rather than housing pricing problem. And in this case, if you have a number of features of a house, you want to predict whether the house will be sold within the next 6 months or not. So it's a classification problem now. So that would be a classification problem. And as we saw, we can come up with quite a lot of features, maybe 100 different features of different houses. For a problem like this, if you have to include all the quadratic terms, all of these will have a huge number of created features. So including all the quadratic features does not seem a good idea because that's a lot of features and you might end up overfitting the training set. If you consider only the multiplication of two variables, that means prime variables, as new additional feature, the number of features will increase in the order of n square. And if it is a multiplication of three variables, the order will be n cube. In case of two variable, in the particular problem, if the primary features is 100, then 5,000 additional feature will be added. If you multiply three primary variables, the order will be n cube, and the additional feature will be 1,70,000. The computational task will be very lengthy, and that's why this kind of problem, is almost infeasible. Here is another example. Let us consider the problem of computer vision, and suppose you want to use machine learning to train a classifier to examine an image and tell us whether or not it is the image of a car. Let's zoom into a small part of the image, like that area where the little red rectangle is. It turns out that where you and I see a car, the computer sees is this matrix, which is a grid of pixel intensity values that tell us the brightness of each pixel in the image. So the computer vision problem is to look at the matrix of pixel intensity values and tell us that these numbers represents the door handle of a car. Concretely, when you use machine learning to build a car detector, what we do is we come up with the level training set with this kind of matrix. Let us say if you level examples of cars and if you level the examples of things that are not car, then we give our training set to the learning algorithm to train a classifier. And then we test it and show the new image. What is the new thing? And hopefully recognize that that is a car. To understand why we need non-linear hypothesis, let's take a look at some of the image of car. We might feed to our learning algorithm a couple pixel location in our images so that pixel 1 and pixel 2 locations we can recognize. Let's plot a certain point depending on the intensities of pixel 1 and pixel 2. So let's take a different example of car and here look at the same 2 pixel location, and that image has a different intensity of pixel 1 and the different intensity of pixel 2. So it ends up in a different location on the figure. And then let's plot some negative examples as well. If we do this for more and more examples using the pixel to denote cars, the points may look like this one, where there is a decision boundary, and you can easily see the decision boundary is nonlinear. Now suppose we use just 50 by 50 pixel image where our feature vector x lists all the pixel intensity. You know that the pixel brightness of a pixel 1 and the brightness of pixel 2 and so on down to the pixel brightness to the last pixel. So we have n equals to 2500, and that is computationally very expensive. So simple logistic regression together with adding in maybe the quadratic or cubic features, that's just not a good way to learn computer nonlinear hypothesis when n is large, because you just end up with too many features. In the next few slides, I would like to tell you about neural network, which turns out to be a much better way to complex hypothesis. Neural networks are a pretty old algorithm that was originally motivated by the goal of having machines that can mimic the brain. In this lecture, I would like to give you some of the background on neural networks so that we can get a sense of what we can expect them to do, both in the sense of applying them to modern day machine learning problems, as well as for those who might be interested in the big AI dreams of someday building truly intelligent machines. The origins of neural network was as algorithm that tried to mimic the brain. Neural networks came to be very widely used throughout the 1980s and 1990s, and for various reasons, popularity diminishes in the late 90s. But recently, neural networks have had major resurgence. One of the reasons for this resurgence is that neural networks are computationally somewhat more expensive algorithm, and computers became fast enough to really run large-scale neural networks. And because of that, as well as a few other technical reasons, which we talk about later, modern neural networks today are these state-of-art technique for many applications. So when you think about mimicking the brain, the human brain does so many amazing things. The brain can learn to see, process images, learn to hear, learn to sense of touches, etc. You can learn to do math, to do calculus, and the brain does so many different amazing things. If you want to mimic the brain, it seems like you have to write lots of different pieces of software to mimic all these different fascinating, amazing things that the brain does. But the way the brain does all these things is not with thousand different programs, but instead with just a single learning algorithm. This is just a hypothesis, but let me share with you some evidence for that. This part of brain, that little orange part of the brain is your auditory cortex. And the way you understand my voice now is that your ear is taking the sound signal and routing the sound signal to your auditory cortex, and it is allowing you to understand my words. Neuroscientists have done the following fascinating experiment on animal brain. Where they cut the wire from the ears to the auditory cortex and then rewire so that the signal from eyes from the optic nerve eventually gets relative to the auditory cortex. If you do this, it turns out that the auditory cortex will learn to see. If you do this to the animals, they can perform visual discrimination, and that is, they can look at images and make appropriate decision based on the images, and they are doing it with the same piece of brain tissue. Previously, ears were processing, now eyes are processing the input. Because of these and other similar experiments, these are called neural rewiring experiment. If same piece of physical brain tissue can process sight or sounds, then maybe there is a single learning algorithm that can process sight or sound, and maybe of needing to implement a thousands of different programs or thousand different algorithms to do thousand wonderful algorithms and programs that brain does. Maybe what we need to do is figure out some approximation or to what the brain learning algorithm is and implement that. So in the next few slides, we will start diving into the technical details of neural network so that you can apply them to modern day machine learning applications and get them to work well. From this slide, I want to start telling about how we represent neural networks. In other words, how we represent our hypothesis or how we represent our model when using neural networks. Neural networks were developed as simulating neurons or network of neurons in the brain. So to explain the hypothesis representation, let's start by looking at what a single neuron in the brain looks like. Your brain and mind is jam-packed full of neurons like this. And neurons are cells in the brain, and the two things they draw attention to us. First, that the neuron has a cell body, there is a cell body, and moreover, the neuron has number of input wires. These are called dendrites. These are the input wires. You think of them as input wires, and these receive inputs from other locations. And the neuron also has an output wire called the axon. This is the output wire. And this output wire is what it uses to send signals to other neurons or to send messages to other neurons. So, as a simplistic level, what a neuron is, it is a computational unit that gets a number of inputs through the input wires and does some computation, and then it sends output via axon to other nodes or to other neurons in the brain. We are going to model a neuron as a logistic unit. So when I draw this maroon colored circle, they are analogous to body of neuron. And we then feed the neuron a few inputs via these wires called input wires, and which are analogous to dendrites. And the neuron does some computation and the output some value on this output wire, which is analogous to our axon. And we use the bias unit, we add the bias unit, which is x0, and this x0 is always equal to 1. As usual, the x vector is the input vector containing x1, x2, x3, and also the bias unit x0. So this is very simplistic. Rather, we call it vastly oversimplified model of the neuron in the brain. Finally, one last bit of terminology. When we talk about neural network, sometimes we will say that this is a neuron or artificial neuron with a sigmoid or logistic activation function. So this activation function in the neural network terminology, this is just another sigmoid function, and the function as defined earlier is equal to 1 over 1 plus e to the power minus z. Now calling to the theta parameters, we call it parameters, but in neural network literature, sometimes you might hear people talk about the weights of the model, and weights are exactly the same thing as parameters of the model. So this represents a very simple form of neural network. Now we shall discuss about the formal definition of neural network. That means what are the different nodes that we have to add for a neural network. And this is the minimum configuration of a neural network where there will be three layers: layer 1, layer 2, layer 3. And apart from the different X, that means the feature of different examples, each and example has a number of features, and those are x1, x2, x3. And we have to add a x0, the feature x0, which is actually bias unit, and the value of x0 is always 1. So these four nodes, x0, x1, x2, x3, is giving the output to the another node, which is called a1, a1, a2, a3. And this is the second layer. So a superscript 2, 1. So the output of this A function, that means these are called activation unit. This output of this activation unit becomes the input for the next layer. And again, there is a activation unit for A1, 3. So this is an activation unit, and this is actually nothing but the hypothesis, output of the hypothesis. So this is our X, and this is our hypothesis. So these hypotheses will be compared with the Y value, given value, and then we have to calculate back the thetas. So we just today will describe the network, not the learning process. How the network will learn will be discussed in the second part. And one thing that I have to mention that apart from this A1, A2, A3, like the first layer, you have to add a A02. A02 is actually the bias unit for this layer. So this value is also 1. A02 is also 1. So this constant bias unit you have to add it in different layers. The output of the layers will be calculated from the previous nodes, but this is a new node which is given a value of 1. So this is the basic structure of a neural network. And we will, as we proceed, we always discuss about this kind of network and maybe a different type, but this is the minimum and basic network. So this is called input layer, and this one is the output layer, and the middle one is called hidden layer. The name hidden may not be appropriate for neural network, but in the literature, always the layer between input and output is called hidden layer. It can be single layer, it can be multiple hidden layer. So let us now discuss about the some symbol like index of example is I. This symbol we have already used in the lecture 2 and 3. The number of example is m, but the index is I. For example, in this case, you see the I is the index of example. It means the x0, x1, x2, these features are for ith example. Then index of feature j, this is j value 0, 1, 2, 3. So there are three features and one bias unit, in total 4. Then number of examples, these I value can go up to m. is starting from 1, it goes up to m. So number of examples is m, number of features is n. In this case, n is equal to 3, but the including the bias, it is 4. But the feature number, when you say what is the number of feature, we'll call it 3. Index of layer, for example, this is p equal to 1, p equal to 2, p equal to 3. P is called the index of layer, and the index of unit. For example, in the first layer, the q1 is 0, q1 equal to 2. So this is the index of unit, qp. P is the layer number. So q1, q2, q3. So q1 equal to 0, q2 equal to 0, q3 equal to 1. So in this way, you can define the different unit. This one unit, this second unit, the third unit, the fourth. In this case, incidentally, the number of units are same in the input layer and hidden layer, but it may not be the case in every example. Number of layer is NL. For example, in this case, there are 3 layers, so NL will be 3. Number of units in a pth layer, SP. How many layers, how many units in certain layer is defined by SP. For example, S1, S1 means the number of units in first layer is equal to 3. Similarly, X3, 5 is the third feature of fifth example. So this is your third feature and I may be 5. So fifth example, third feature, if you generalize it, we will call it XJI, jth feature of ith example. Similarly, A12, this unit is called first activation unit of second layer. So if I generalize it, I should say the AQP of P, that means QPth activation unit of Pth layer. QP means, for example, Q1, Q2, Q3. So Q1, Q2, Q3, and P is the your layer number. So P is the layer, QP is the your unit index for Pth layer. So this is basic description of a simple neural network where there is one input layer, one output layer, and one hidden. This is the final form of neural network. We have 3 layers, but the diagram shows the different steps of calculation. For example, the 4 input units, actually 3 input units and one is X0 unit. So these units are the inputs, and with the multiplication of theta, we'll add up together and you'll get the z, and z is fed to your sigmoid function, and the output is called A2 activation. So previously we have shown the line straight coming from the unit up to the activation point. Actually, there are 2 steps. One is first of all a summation of all the theta with x, that will make z, and z is applied to the sigmoid function, and the output of sigmoid function is the A. So that's why we have draw this diagram similar for the level 3. You see z1 and then z of z1. So as we mentioned earlier, this is called layer 1, and the number of units in layer 1 is 3, 1 to 3. X0 is the out of the unit because this is an bias unit, separate unit. And then the layer 2, there are also 3 units, A1, A2, A3. Similarly, there is a bias unit, A0. And this is your third layer, where S3 equal to 1. S3 means number of units in layer 3. Let us concentrate on theta. So how to write the subscript and superscript of the theta? First of all, the superscript should be the level. For example, These all thetas are coming from level 1, layer 1. That's why the superscript is P. Then the subscript. Subscript starts from the other end and ends at the beginning end. So the remote end first, for example, QP plus 1, Q is the index of the unit in the first unit, second unit, third unit, but this is P plus 1. P plus 1 means the next level, next layer, and from that unit it is connected to the beginning unit. So that's why the subscript should be 1 0. 1 is the other end, this is the one first, your first unit, and it is coming to the 0 unit. That's why theta 1 0. You notice that theta is here, it is a capital theta, it's not a small theta. Previously, for logistic regression, we also use theta. In linear regression, we use theta. Those thetas are a small theta, and this is the uppercase theta. Similarly, if you check the other naming convention, for example, theta 20, why it is 20? Because 2 is the QP plus 1, that means other end node number, and this is the beginning end node number, so theta 0. For example, this 2 3. Why this 2 3? Because it is coming from the second node, and it is from coming to the second node, and it is from the third node of the layer 1. So the next layer node number of the next layer should be first, and the node number of the previous layer should be second. So 2 3, not 3 2. Similarly, for example, 2 2. Why 2 2? Because 2 to 2. So 1 2, because this is going to 1, the next layer unit number, and 2 is the unit number of the first layer. In this way, we have to define the superscript and the subscript. Similarly, for second layer, the layer connected to these thetas, theta 1 0, because 1 is the unit number of the next layer, and this is 0 is the unit number of the first layer. So 1 0, 1 1, 1 2, 1 3, and every time the superscript is within bracket 2. It means it's related to the level 2. And you notice that this is the sigmoid function. The J1 is the input to the sigmoid function, and output is nothing but A1, A2, A3. In this case, only single units, only A1. And this is also called H theta xi. So if you are given the different features of a certain example ith example, then you can proceed one step after another, and finally you get the A13, which is your H theta xi. If you notice the theta nomenclature, the theta 1 matrix, this theta is nothing but a matrix of the first layer. There are 3 elements in each row, and the number of each column, and the number of rows is 4. So the matrix with theta Q2, Q1. Q2 is the second layer, and Q1 is the first layer. And Q2 starts from 1, 2, 3, 4, etc. up to S2. And Q1 starts from 0. You see the Q is this stage number, this node number. So it starts from 1, goes up to 3. So 3 is the number of units. And in this case, Q1, it starts from 1, it goes up to 3. So starting from 0, it goes to 3. And Q2, starting from 1, goes to 3. So this is the writing convention of theta. Now let us discuss about the relations between Z and A. The Z and A is related by a sigmoid function. You see, A1 is equal to sigmoid function G of all the summation, this summation representation. So this within the bracket, this term, we call it actually Z. You see Z, this is the Z. So if we replace this whole term with a Z1, then in this case we can put Z1. So the previous, the this equation now becomes Z1. So A1 2, we can call it Z, G of Z1 2. So because Z1 is the input and G of Z1 is the output, which is nothing but A1. Similar for the other nodes. So let us now discuss about the vectorized implementation. How we can implement the neural network equations so that we can solve by vector. First of all, the steps in this implementation. First step is you have to define all xi with A. A is the matrix, it's a vector, but it contains different elements like A11, A21, A31, etc. Similarly, Xi is the vector, but it contains different features like X1i, X2i, X3i. I could be any value between 1 and m. So it includes x0. First of all, you have to define all the features, then one term should be your x0. The second step is actually this equation. If I go to the final equation, this equation, that means all the z is related by the matrix, theta matrix multiplied by your x matrix. So if you multiply this row with this column, that will give you Z12. Similarly, Z22, Z32. So theta 1, this is the theta 1 matrix. Theta 1, that means the theta related to first layer. The first layer thetas, all these elements, multiplied by A1. This is the nothing but A1 because we are in the first layer A1. So if you multiply these two, then it will be Z2, Z in the second layer, Z1, Z2, Z3. So this is the equation that you have to solve. First of all, theta 1, from the theta 1, then from the A1. A1 is nothing but X1 actually. So you just multiply them two, you will get Z. What is the next step? Next step is A2 equal to G of Z. This is the summation term, and if you apply the sigmoid function over the summation term, that will give you the activation term, which is A2. Because we are going to the second layer, A2 means second layer. Third step is modify A2 by adding A0 to equal to 1 because this contains only from 1 to up to n number of units NP and sorry SP. So this equation will give you only the units starting from 1. So you have to add A0. Then this A, that means your A2 plus A0, that means one element is added. So this is the final modified A2. And modified A2 multiplied by theta 2. It's not theta 1, you see. Theta 2 multiplied 2 will give you Z3 like the previous one. Next is apply Z3 into the sigmoid function. You will get A3. And once you get A3, this is not by but H theta xi. So this is your vectorized implementation of the neural network, and we call it forward propagation because we start from the input and we go to the output in the forward direction. There is another term which is called backward propagation that will teach you in the next lecture. But up to this, we have discussed how to calculate different quantities like A, then Z, etc. in case of neural network, if following the starting point up to the last one. So if you apply this vectorized form, then the life will be very simple. You don't have to write the loops and etc. There are other network architecture. This diagram shows there are four layers, layer 1, layer 2, layer 3, layer 4. And layer 1 is the input layer and layer 4 is the output layer. So rest of the layers like layer 2 and layer 3 are the hidden layers. When the problem becomes complicated, that means the nonlinearity inherent nonlinearity of a problem. When it is very high, then the number of layer required in the hidden layer should be greater than 1. Throughout the discussion, we have shown you how to calculate the hypothesis, that means h theta xi given x0, x1, x2, and x3. That means inputs. If you have inputs through the neural network using the different thetas and activation function, all these sigmoid function, applying sigmoid function, you can calculate up to output. The important topics that we have not discussed yet, how to calculate the theta, because we are going to apply the optimization technique to find out the thetas. There are a lot of thetas in the first layer, also the second layer. So our next problem is how to calculate the thetas. The topics includes the back propagation algorithm, and in the back propagation algorithm we will see the method of finding the thetas. But in this lecture we will not cover that part. We just give you the impression how the neural network works. So we'll continue our lecture by showing you the situation where nonlinear problems are solved by neural network. Let us see the case of a gate XNOR. XNOR is a logical gate, and if you draw the output 1 and 0, the points will be over there. These are the X are the 1, output 1, and circles are the your 0. So when x1, x2 both are 1, 1 or 0, 0, then it is output is 1. This is actually similar to this kind of classification problem. Where classification problem will be complicated because this is a nonlinear boundary. Decision boundary is nonlinear. That's why the problem is not very simple. But using the neural network, you can easily get the nonlinear decision boundary. In case of X NOR, the logical symbol is x1 x NOR of x2. And this is actually nothing but not of x1 XOR of x2. So if you take XOR and then you take the not, then it will be x NOR. So these are the y equal to 1 case and these are the y equal to 0 case. And if you draw the truth table will be like this. When both are 0, then output is 1. When both are 1, the output is 1. But if they are dissimilar, then the output is 0. So mathematically, we write this equation for case of x naught, x1 XOR of x2 with a not. So that is your x naught. And if you expand this one, you will end up with this equation x1 and x2 or x1 not and x2 not. Let us now see a network that simulates AND gate. The AND gate, the inputs are 0 or 1 and the logical equation is y equal to x1 and x2. So there are two inputs, x1 and x2, and the output is actually given y and predicted h of theta x. And you have to add a bias unit, and then you have to go through the process of neural network in order to find the thetas. And let us say the theta comes out as minus 30 plus 20 and plus 20. So we'll write the equation for hx as g of minus 30 plus 20 multiplied by x1 plus 20 multiplied by x2. So this is our theta 101, theta 111, and theta 121. So these are the theta metrics, and then we know the sigmoid function. If we put the different combination of x1, x2, then we'll get the value of z, and that z will tell us whether it is close to 1 or it is close to 0. So this is a truth table for AND gate. When input are 0, 0, you put 0, 0 there. and then minus 30, g of minus 30, which is far from the 0, so it is, sorry, minus 30 in this direction, so output will be 0. So when you put x1 equal to 0 and x2 equal to 1, then output will be g of minus 10. G of minus 10 is again, it is close to 0. And 1, 0 is again g of minus 10. So this is also 0, but when you put 1, 1, then these two will be plus 20 plus 20, so minus 30 plus 10. So g of plus 10 is 1. So you see the output values 1, 1, 1, 0. So when both are 1, then it is 1. Other than that, it is always 0. So it is actually an AND gate. So the logical gate AND can be simulated or can be implemented by a neural network if we can get the proper value of theta. Let us now take the example of not x1 and not x2. Whether a neural network can be designed to solve this logical equation. So this is the diagram for neural network. X1, x2 is the input and h theta x is the predicted value and 1 is the bias limit. So if you can get the values of thetas, you can get the relationship between h theta and x1 and x2. Let us say we obtain the value as plus 10, minus 20, minus 20. So h theta will be g of plus 10, minus 20 x1, minus 20 of x2. So this case, theta 1, 0, theta 1, 1, and theta 1, 2 will be those values. And if we put these values of x1 and x2 combination into the equation and get the value of z, the term within the bracket is the z, and then we can get whether it is high value or it is low value, whether gz is 1 or gz is close to 0. So this is the truth table or this is the output table. So if x1 and x2 are 0, 0, then output is g of plus 10. So g of plus 10 is close to 1. Then 1, 0, 1, it is g of minus 10, 0 and 1. So this is 0 and this is 1, minus 10. Similarly, 1, 0 is also minus 10. And 1, 1, then it is minus 30, which is also 0. So the output says that the values of x1 and x2, if they are 0, 0, then the output is 1. Otherwise, it is 0. This is the simulated result of this particular logical operation. So if we take the OR function simulation of OR function, and let us say we solve the weights like minus 10 plus 20 plus 20. So g of minus 10 plus 20 x1 plus 20 x2 will be the h of theta. And if we apply those in a sigmoid function over there, if we apply in a sigmoid function, then the outputs will be g of minus 10, g of plus 10, g of plus 10, g of minus plus 30. So it is 0, 1, 1, 1. So when any one input is 1, then output is 1, which is actually the OR function. So let us now see the implementation of XNOR gate with AND and OR. We have already discussed about the output equation, and by gate we can have this solution. Two AND gate, the input is inverted, and then the two output of these two gates are OR together, and you'll get the NOR XNOR gate. So if we add these diagrams, for example, this is the operation for AND gate. This is the operation for not x1 and of not x2, and this is x1 or x2. And if we apply these three network in a combined network, then it will be something like XNOR. For example, this is the green network, and we apply with the yellow one, and we'll get the another network. So the output, this output is AND output, and this output is not x1 and not x2. The weights are collected from those figures, and if you then OR them together, OR them together with a bias unit, then the output will be your the finally XNOR operation. If we solve the truth table when the x1 x2 is 0 0, this a1 is the AND gate operation, so this is AND. If A2 is the not X1 and not X2, that is your 1000 second network, and the third network is the red network. So apply the OR gate that we have already solved. The OR gate for these equations, if you put together, this will give you 1, this will also give you 0, and that will give you 0, and that will give you 0. If you put the values 0, 1 into this equation of g theta, gz, then you will end up with 1001, which is nothing but the output of XNOR. So this network, the simple neural network, is implemented for XNOR. XNOR is a very complicated actually problem because the decision boundary is not linear, and this kind of nonlinear cases can be easily solved by neural network. In this part of lecture, I will discuss how to use neural network to do multi-class classification, where we may have more than one category that we want to distinguish one from others. The way we do multi-class classification in a neural network is essentially an extension of the one versus all method. So let us say that we have a computer vision example where instead of just trying to recognize car or non-car, let us say we want to recognize four categories of objects. So given an image, we want to decide whether it is car or a park or a bus or a shop. If this is the case, what we do, we would build a neural network with four output units so that our neural network now outputs a vector of four numbers. And what we are going to try to do to get the first output unit to classify the image of car, yes or no. The second unit to classify the park, yes or no. The third unit to classify the image of bus, yes or no. And the last unit to classify the image of shop, yes or no. Thus, when the image is of car, we want output of 1000, and when the image is park, we want the output 0100, and so on. So this is just like the one versus all method that we talked about when we were describing logistic regression. And here we have essentially for logistic regression classifier, each of which is trying to match is one of the four options. Whereas previously we had written out the levels as y being an integer from 1, 2, 3, or 4. Instead of representing y this way, we are going to represent y as follows. Namely, yi will be either 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, depending on what are corresponding image xi. So one of the training example will be one pair xi yi, and so xi is the image with one of the four objects, and yi will be one of these vectors. So in this way, we can easily train the neural network to distinguish one of the images in one of the output nodes. So by this, we wraps up our discussion on how to represent neural network status on a hypothesis representation. In the next set of lecture, let us start to talk about how to take training set and how to automatically learn the parameters of the neural network. So thank you very much.